In this video, we're going to look at the fundamental theorem of calculus and the definite integral. Now, the exercise in the textbook looks at the fundamental theorem of calculus as well as relating the definite integral to the area under a curve. What I'm going to do is just focus on this first part because this is what you need to know to be able to do the exercises in 11E. This second bit that ties the definite integral to the area under the curve, I'll deal with at the start of 11F. Okay, so the fundamental theorem of calculus is this formula here. And the reason it's called the fundamental theorem of calculus is that it linked what was up until then, when they came up with the idea, when they discovered the link, the two different areas of differential calculus and integral calculus. And when they realised the relationship between the area under the curve, which is our integral calculus, was related to differential calculus, which was finding our derivatives and our antiderivatives, it was a really major idea. So for us, it's kind of a no-brainer because we've taught it to you all the way through. But when they found the link, it was a massive thing for mathematics. So anyway, this is the fundamental theorem of calculus. You'll never need to be able to repeat it. You will just use it. It's this bit here. So if f is a continuous function on an interval from a to b, a closed interval from a to b, so that includes a and b, then the definite integral from a to b of the function is equal to the antiderivative of this original function with your b terminal value substituted in, take away the antiderivative of this f function with your a value substituted in. And you actually have to take away the whole of this section here. So let's have a go at an example. So let's look at using the fundamental theorem of calculus, which normally in the textbooks or in a question, it'll just say evaluate the integral. So using the fundamental theorem of calculus is also known as evaluating the definite integral. Now these antiderivatives, f of x, we can use any antiderivative of the original function as we like. And so for simplicity's sake, we're just going to use the antiderivative with c is equal to 0, so we don't have to include a plus c with any of our antiderivatives. Okay, so let's have a look at an example here. So we're going to integrate between 2 and 3 the function f of x dx. So here's our to-do list. First, we're going to find the antiderivative of this particular function. And so the antiderivative of x is x squared on 2, and I put it in square brackets like this. The brackets have to be squared, and I put the two terminal values, the lower terminal at the bottom 2 and the upper terminal 3. I actually take them exactly as they are written here. Sometimes it's not always the smallest one on the bottom and the largest one on the top. So whatever it says at the top goes at the top, and whatever it says at the bottom goes at the bottom. So we've found our antiderivative. The next thing that we do is that we find, we find our antiderivative with the top value substituted in. So here's our antiderivative, here's our top value. So now I've gone for curved brackets. So where the x is, I'm putting a 3. So 3 squared on 2. And then I take away the whole of the bottom function. Now, the reason that I've got this here in green is that the most common mistake that students make when they're evaluating definite integrals is they put a minus sign like they're supposed to here. But can you see what would happen if you didn't have these brackets around the last substitution, the antiderivative with the bottom value substituted in? The most common mistake is that people put a minus here, and then whatever else comes along, they forget that they should be subtracting that value. So it's a really good idea to put minus and brackets around this second bit. Okay, and then the final step is that you simplify your answer. So 3 squared is 9 on 2. 2 squared is 4 on 2. So the answer is 5 on 2. Let's have a go at another example. So this time we're going to integrate x squared plus 2x plus 1 between 0 and 2. So our first step is to find the antiderivative. So the antiderivative of this, x squared is x cubed on 3, 2x is x squared, and 1 is x. And then I put my two terminals exactly as they appear here, 2 on the top and 0 on the bottom. And then I substitute my terminals in. The top one first, so I'm going to put 2 where these x's are, and then take away the whole function with 0 substituted in. And then finally, we're going to simplify all of these values. So we've got 2 cubed is 8 on 3, plus 2 squared is 4, plus 2. Take away all of that gives you 0. So to work all this out together, we've got 8 on 3 is 2 2/3 plus 6, so it gives us 8 2/3. So the next thing that we're going to do is we're going to look at some properties of definite integrals, and we'll revisit these when we get to the area under the curve, and they'll start to make a little bit more sense. But we're going to look at these just purely from an algebraic point of view. So our first property that we're going to look at is the fact that if you integrate from a to a for f of x, you actually get a 0. So let me show you how that works. If you actually integrate by finding f of the antiderivative and substituting in your top and your bottom, what you'll notice is you'll get f of a minus f of a, which is obviously 0. This next one, with the definite integral, we've got a constant multiplying the function, and when we've been working with indefinite integrals, we could just bring that constant out the front. So we can still do that with definite integrals. Okay, you can just bring the k out the front. And to show you that that actually works, what I've done here is I've done a comparison between the integral from 1 to 2 of x versus the integral from 1 to 2 of 10x dx. And if I go through and work both of those out, there's your antiderivatives. The one with 10 has a 10 in the front. You substitute the two values in the top and the bottom each time. I should have a little line down here to show you that that's actually one versus the other. You can see that there is still a common factor of 10 all the way through on that second one. And so what we've got, this is our integral from 1 to 2 for x, and that is exactly the same as our integral that we've got here with our 10 multiplier that was inside the integral, now outside the integral. So if it was inside the integral, you can pull it out to the front. That's perfectly correct. And then the last one I want to show you is what happens when you swap the terminals around. And this might seem a bit of a weird thing to do, but it will make more sense when we look at the area under a curve. So what you get if you swap the position of A and B around, the answer that you get for this is in fact the negative version of the swapped around terminals. So let me show you here. Get out the way. So we've got the original version here from A to B, so it's f of B minus f of A. So now I'm going to swap the terminals, and I now get f of A minus f of B, which if I do some algebra, multiply the whole thing by minus 1, gives you a swapped sign. So this was positive f of A Multiplying it by negative, you can have it as negative f of a, and this was negative f of b, and you can have it as positive f of b. So now I can write these two round the other way, so this one first, and then what you've actually got is negative of the original one that you got before. And so you end up with the relationship that if you swap the terminals, you get the same answer, same size answer, but with a negative value. The final property of definite integrals that you will need to use in 11E actually relies on understanding that you can use the definite integral from A to C, to represent the area under the curve from A to C. And what this property says, that the integral from A to C, all that area under the curve, is equal to the integral from A to B, this yellow area here, so the yellow section, plus the area from B to C, the blue section, as long as, that's the blue section there, as long as B is somewhere in between A and C. So that's our B there and our B there. As long as you're splitting it so that the split is actually an x value that fits in between those two endpoints. So now let's do some questions using these properties. So using the properties, and here's an example. If the integral from 2 to 3 of f of x is 5, find the integral from 2 to 3, so same terminals, of 4 times f of x. Now, this is multiplying f of x, so we know we can bring that out to the front. So it's 4 times the integral. We know that the integral itself, the integral from 2 to 3 of f of x is 5. So I can replace that integral symbol with the 5, and it's 4 times 5 is 20. Okay, so the next one, find the integral from 2 to 3 of f of x plus x. Okay, so this is a little bit weird, dx, so we're integrating this whole thing all together. So what we're going to do is we're going to split it into our integral that we've got up here, this little yellow section here, and then we're going to integrate the section with plus x, so just this bit here. When we do that, we know that the integral from 2 to 3 of f of x is 5, so we just replace that value there, and then we evaluate that particular integral step by step by finding the antiderivative, substituting in our 3's and taking away our 2 substituted in, tidying up with our fractions. So we've got 5 plus 4, 9 on 2 minus 4 on 2, 5 plus 5 on 2. So the 5 is 10 on 2 plus 5 on 2 is 15 on 2. Let's have a look at some more. So sticking with our same integral, from 2 to 3 of f of x is 5. Find 3 to 2 of f of x. So the terminals are swapped here. So when we swap the terminals, we get the same answer. So the answer is going to be 5, but because the terminals have swapped, we're going to have a negative number in the front of it, so a negative symbol in the front, so it's going to be minus 5. And then finally, another one where we are integrating f of x from 2 to 3, so that's exactly the same, plus 1. So we're going to put this down as being equal to the integral, this section here is 5. We've got plus 1 here in our integral, so we're going to add the integral from 2 to 3 of 1 dx and work it out from here. So 5 plus the integral of 1 is x from 3 to 2, so it's 5 plus 3 minus 2, which is 8 minus 2, which is 6. Alright, and finally, given that the integral from 0 to minus 5 of f of x is equal to 1, and 0 to 2 of f of x is equal to minus 4, find the integral from minus 5 to 2 of f of x. Now the easiest way to do this is to think of these as areas underneath the curve between these two terminal points. So let's first of all put all of our terminal points, but we've got minus 5, 0 and 2. So let's put those onto an x-axis. There we go. So we've got minus 5, 0 and 2. So what we've got to do is find from minus 5 to 2. So let's split this using our property where as long as there's a value between these two. So we've got minus 5 on the end, we've got 2 on the top, and 0 actually fits in the middle. So we can actually split our integral going from, in the correct order, from smallest to largest, negative 5 to 0 of f of x dx, and 0 to 2 of f of x dx. Oops, f of x dx, there we go, move that to there. Okay, so now we can use what we know. This is this with the terminal swapped. And we know that with it 0 at the bottom and minus 5 at the top, it's a 1. And so we know we can rewrite it so that it's the negative version of what we've got. So if we put a minus sign out the front here, not being very clear, if we put a minus sign out the front here, we can have this as the integral from 0 to 5, like we've got up the top. And then we can replace that number, we can replace that integral, sorry, with the number 1. And then we've also got our second integral that we already know is minus 4. So if we substitute in, what we've got is a negative version of our first integral. So our answer is in fact negative 1 minus 4, which gives you negative 5.